Hello friends, this is Dr.V Siva Nagaraju from IARE. Today we are going to discuss noise analysis in AM system. So in previous sessions we discussed different noise analysis like DSB, SSB. So today we are going to discuss AM. So AM means amplitude modulation. So we are going to discuss how the noise is calculated in AM system. Okay. So first we take the standard AM wave is S of t, which is equal to AC of 1 plus Ka m of t into cos 2 pi fct. We know that S of t is the amplitude modulated wave. AC is the amplitude of the carrier signal, where Ka is amplitude sensitivity, m of t is message signal, Fc is a carrier frequency. So this is our standard AM wave. So from that standard wave, we are taking the average power of AM wave. That means in this session, we are going to figure out merit of a AM system. Okay, so that means at the receiver point, we are going to calculate. So first to take the average power of AM wave. So PS, which is equal to AC by root 2 whole square. So here how this coming is you can extend this one, you get to AC plus AC K m of t into cos 2 pi EFCT. We know that AC is carrier amplitude. So for the average power, we take the RMS value AC by root 2 whole square plus and the second one is AC, again it is a carrier. So for the power AC by root 2 Ka m of t whole square. So after squaring the terms, you get the first one is AC square by 2 and second one is AC square Ka square m square of t divided by 2. So here m square of t taken as the power of the message signal. So where p is the power of the message signal. So finally PS, the average power of AM, is equal to AC square into 1 plus Ka square P divided by 2. Okay. So that is the average power of AM wave. And you take another one is noise. That is average power of noise in the message bandwidth is W N naught. We know that the message bandwidth is 2W and noise spectral density is a naught by 2. So those two is going to cancel. Finally, we get the noise power in the message bandwidth is W N naught. So the SNR. So SNR channel in AM is taken as AC square into 1 plus Ka square P divided by 2W naught. That means here SNR, average power of that signal divided by average power of the noise in the message bandwidth. So that is SNR. So signal to noise ratio taken as AC square into 1 plus Ka square P divided by 2W naught. So here we are going to assume some band pass noise is mixed with that AM wave. Why? Because after transmitting the signal into the channel, the noise will going to adds up. So the combination of that signal plus noise we denote as V of t, which is equal to S of t plus N of t. So N of t is the noise. It is a narrowband noise which is going to add with our signal S of t. So N of t, narrowband noise, you can represent in terms of in phase and quadrature terms. So N of t, which is equal to N I of t into cos 2 pi fct minus N q of t sin 2 pi fct. So there is a narrowband noise in terms of both in phase and quadrature. So finally the V of t, which is equal to AC into 1 plus Ka m of t into cos 2 pi fct. That is our S of t. It is our S of t. What is S of t? Amplitude modulated wave. So amplitude modulated wave plus narrowband noise N of t. You are going to write that one. In the next step, we are going to take a common of those customs. Why? Because here the V of t contains AC into 1 plus Ka m of t cos term, this cos 2 pi fct term, plus n I of t cos 2 pi fct minus n q of t sin 2 pi fct term. So here I am going to take common these cos terms. So we got AC plus AC Ka m of t plus n I of t into cos 2 pi fct minus n q of t sin 2 pi fct. So the last term n2 of t term is the quadrature noise component. Okay. So this V of t, which is going to apply that demodulator, so you get the output d of t taken as AC plus AC Ka m of t plus n I of t whole square. So the first term is AC plus AC Ka m of t plus n I of t whole square, and the second one is nq of t, that is our quadrature component, quadrature noise component. So we are going to neglect that nq of t, and finally we got d of t, which is equal to AC plus AC Ka m of t plus ni of t. Why? Because we are going to neglect nq of t term, so this is going to zero term in the second one, and first one is the square, and this root is going to cancel. Finally you get AC plus AC Ka m of t plus ni of t. This is the output of our demodulator. So the average power of demodulated signal is PSO, represents PSO, which is equal to AC Ka m of t by root 2 whole square. Why? Here the carrier amplitude is there, so taken as AC by root 2 and Ka m of t whole square. So m square t taken as the power of the signal, so that is considered as P. So finally, the average power of the demodulated signal, which is equal to AC square Ka square P divided by 2. And the average power of noise at the output is PNO, which is equal to W N naught 2. Why? Because we are going to find the figure of merit of this AM system. So FOM, figure of merit, which is equal to this SNR output by SNR channel, we are going to calculating these terms. So that's why we take in the average power of this demodulated signal and average power of this noise at the output. So take in the relation between output and the channel SNR. So we get the figure of merit. So finally, the figure of merit, which is equal to AC square Ka square P divided by 2 WN naught. That means signal to noise ratio at the output in AM system. That means the demodulated output taken. Output means at the end. So at the end means you taken out from the demodulator. So SNR output, signal to noise ratio output in AM system, which is equal to S square K square P divided by 2. That is nothing but our signal and the ratio with the noise W and naught. So finally that one. So the figure of merit, which is equal to signal to noise ratio to the output. Signal to noise ratio is the output in AM system to the signal to noise ratio channel in AM. So we are going to find SNR O, that is output, and SNR C in channel. So we are going to substitute those two. So after substituting figure of merit, which is equal to that SNR output in AM divided by SNR in channel. Okay, so we are going to calculate those terms and cancels this 2W0, 2W0. So finally you got Ka square P divided by 1 plus Ka square P. That is amplitude sensitivity. Okay. So this is the figure of merit of AM systems. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.